The role of observers. Is cosmology a philosophical science? Cosmology unavoidably leads to tolerances that possess philosophical and even theological overtones. Inescapably, a cosmological hypothesis is defined with why human beings live in this unique universe and our role as witnesses. After all, if we did not endure, who cares? The physical models of the cosmos have sufficient chinks in their armor for these thoughtful and even metaphysical questions to compress through the rifts. For centuries, the universal answer to human survival has implied that we are more than an occurrence in the cosmos. In recent decades, this approach generally has been named the anthropic principle. Such concepts are very compelling for theologians. Of course, the anthropic method has also been captivating, if not completely impressive, to philosophers. For cosmologists, however, this can often be a troubling area to start in science. We try to stick to data. We try to describe the natural origins of things according to laws and principles. Indeed, we wish to demonstrate by physical law and theory what contrarily seem to be unique accidents or events. One of these is the beginning of human life on a planet some 14 billion years after the Big Bang. Galaxies, stars, and planets did not significantly have to exist. Nevertheless, they are making our continuation possible. The scientific project of defining our behavior has been around for quite a while. Over the centuries, we have fought our way from a geocentric cosmos beloved by the Greeks to a heliocentric cosmos founded by Nicholas Copernicus. We have called the notion of our non-locality in the cosmos the Copernican principle for reasonable ideas. Up until Einstein's time, the Milky Way was used to be the complete cosmos. This resolution was overcome by Hubble's pioneering determination of the distance range of the cosmos. It became apparent that our Milky Way remained a run-of-the-mill galaxy, neither great nor small, but depressingly familiar about the whole cosmos. The non-special situation of our environment has been called the source of mediocrity. Our changing view of the Milky Way galaxy shows how we came at this knowledge of our averageness, familiar or not, and cosmologists still wrestle with our continuation. To settle this issue, we need some guidelines for commonality. Otherwise, we could suggest any bizarre cosmos and fall over the border into science fiction. The most straightforward way to start is by being down to earth, inquiring about our physical reality concerning physics rules. We cannot rely on gravity and biology to justify our reality concerning the entire cosmos. When cosmologists rely on the anthropic principle to justify why we exist, most use a limited version, while a minority use a fixed version. Cosmologists uses the limited version. We simply assume that the cosmos is the way it is because we are here to witness it. This is a tautology, a circular argument, but it nevertheless has some advantages for some solutions. This approach allows the presence of the so-called multiverse, in which many potential cosmos exist that are unwelcoming to our presence. The most advanced assumptions of quantum gravity count extraordinary 10 to the power of 500 realizations of potential cosmos, all separate from each other because their many necessary constants of nature differ. On the one hand, given the unbelievable collection of alternative cosmos in the multiverse, it grows remarkably doubtful that our perceived cosmos should even exist. Nevertheless, it does exist. Furthermore, according to the weak anthropic law, our living has simply selected the precise cosmos. After all, we can simply recognize a cosmos of a particular size old enough for stars and planets in life to have occurred. Nevertheless, is this sort of conception of physics, or is it metaphysics? Because of our continuation, the age of the cosmos must be old enough to provide stars to synthesize carbon, the foundation of biological life. The next reasonable step is to point to how the uses of all the significant constants of nature, which may diversify throughout the multiverse, are defined by the necessity of our presence. Another path to the weak anthropic principle favored by many of my co-workers selects only the tiny subset of so-called pocket cosmo within the multiverse, and this pocket allows galaxies to form and life to develop within these little pocket universes. The expectation becomes vital for scientists, seeing only a little but non-zero value for dark energy today. A sturdy variant of the anthropic principle maintains that life is determined somewhere in the multiverse. Nevertheless, these reliable anthropic discussions are undercut by forming a possibly infinite age for the cosmos, which insinuates that the cosmos expands and contracts forever. Furthermore, we simply observe one of the developments. Much can follow over a long time, and a cosmos that forever renews itself via eternal expansion. In all anthropic disputes, proponents attempt to demonstrate the relationship of human survival to the values of the primary constants of nature. There are at least 3 rival theories on how these conditions came to be. The first assumed a grand designer could have chosen the values. This has great interest to proponents of the intelligent design of the cosmos. Most cosmologists argue emphatically that there is no obligation to entreat such a theory, although eventually it decreases the problem to a question of individual belief. The second option advances to currently unknown physics. For instance, we noticed those general laws could surmise the height division of human beings. Perhaps we only do not still know the laws for traveling in the multiverse. It may be that it takes an endless time to populate the wealth of panoramas rolling underneath the hill of a false vacuum. We possess no reason to speak about the possibilities of our cosmos appearing. The cosmos began in a steady state. It was the expansion afterward that produced the profoundly asymmetric state of material encompassing us. The assumption is that it would take so long for a void to produce this cosmos that it would appear only once. The possibility question is unnecessary. The third option, and to my judgment the most suitable analysis, says that there was no choice at all. We are here because we are hereabouts. This is what must result in an endless multiverse. Some versions of quantum gravity attracted to the complexity of the first conditions to support an infinitude of landscapes and cosmo in the multiverse. If this remained the case, the competition and the conundrum are over. The dice were thrown, and our cosmos was determined someplace in the multiverse. Furthermore, here we stand. Are we individual? That is a different story. Although an endless multiverse cosmos would provide an infinite amount of cosmos like ours, just as an absolute cosmos provides infinite number of stars, planets, and parts of Earth. One can mainly test this theory. Future investigations will measure the shape of space with impeccable accuracy. If the curvature differs from flatness, an ever-expanding cosmos, we will presume unparalleled in human thought. A somewhat closed cosmos would show the finiteness of the area. A somewhat open cosmos would go far near, demonstrating that time is infinite, at most limited in the most common cosmology. This did turn out to be the problem. One would no longer need to request any anthropic principle. Darwinian division or constant expansion. Some cosmologists undecidedly say that the anthropic principle is not yet consistent from the root. It is entirely irrelevant. There is no way to verify how the cosmos might change if we did not exist or match our universe. This is the spirit of American quantum cosmologists. For instance, as an option, he settled cosmic development like the Darwinian belief in biology. Given the massive multiplicity of cosmo, maybe there is a means of natural selection by which one cosmos becomes approved. To explain the evolutionary system, cosmology engages in black hole formation to spawn new cosmo. Physics does not prevent this process of new cosmo from popping into reality. So, therefore, we are obliged to theorize that it may happen if it does transpire. Rich black hole formation offers a potential channel for cosmos production in this proposal. The winner in this universal race that is the most likely cosmos is overflowing with black holes. Our cosmos is not far from this situation. We understand that 1% of baryonic material is in the form of extensive black holes at the most limited point, 0. These per se are not perfect for cosmos production, as they ordinarily are very long-lived. It is their ancestors that might contain the mysteries of nature. It is even thought that the elusive dark matter is in the formation of black holes in which one has a cosmos whose black hole content produces more than 20% of its mass energy content. The massive black holes could be the recognized byproduct of the ultimate nature of a black hole that governed the cosmos. Black hole birth may give a physical means of universal natural preference. However, the underlying assumption that migrating black holes might produce cosmo is highly uncertain. For instance, tiny black holes are believed to evaporate. The smaller the black hole, the more prominent the deflection of space in its environment. If a black hole weighs fewer than the mass of a mountain, something like 100 billion tons, the framework of space near its exterior is ripped apart, and the black hole ejects out mass. It vanishes. Such tiny black holes are described as many black holes and short-lived. Many black holes ruled the universe at the Planck instant. Singularities are at the heart of all black holes. These are possible gateways to different cosmo. Nevertheless, it seems doubtful that many black holes would result in relic universes. Somewhat all the data once included in the black hole is evaporated along with its size. A chief rival hypothesis to this birth by black hole scenario is the concept of eternal expansion of the cosmos. Inflation can replicate itself. It can occur again and again. That is because the quantum hypothesis tells us that the most unlikely events can happen if we wait long enough. Furthermore, if the cosmos is large enough, such unusual events must transpire someplace, so the distance can begin wherever at any time. In an infinite cosmos, this is eternal expansion. That suggests we are not in a particular place, but our perceived cosmos is remarkable. It is the ultimate successor to the Copernican principle. You may investigate whether there are any results of continued enlargement. One of the most remarkable inconsistencies in cosmology is that the universe is dominated by dark energy. All we know is that the universe is quickening, and this unknown energy force is governed. Recall that it was first considered to endure by Einstein to stop the cosmos from falling before the expansion was seen. However, the expense of dark energy is insignificant. The quantum gravity theory applied to cosmology foretells that the presence of this small force is deeply unlikely. One answer is that many cosmo are presented by hypotheses like persistent inflation, with all probable values of dark energy. Ours appears to be where galaxies and stars could form dark energy, where outstanding stars could not appear. Gravity is negligible compared to aversion. The other cosmo were too scorching, or too frozen, or too dense, or too light. Is there a multiverse? Theoretical physics engages with the concept of a multiverse, the organization of an infinitude of universes, including our local achievement, which is a fantastic concept. Is it even in physics to assume the presence of a multitude of coexisting but non-communicative cosmo? There are many hypotheses for the beginning of a multiverse. Still, it is a poor reflection on our modern state of knowledge that none of them are any more reasonable than that, connected to a commonly cited older woman who reached up at the end of a talk on the nature of the cosmos and angrily accused the distinguished speaker, American philosopher William James. She declared that our Milky Way galaxy rests on the back of a giant turtle. This is, in fact, an old-fashioned Hindu myth. Furthermore, what praise is the turtle enduring on? Questioned the bemused speaker. She responded that the solution was evident. There are numerous choices. One is that the cosmos, our cosmos, is individual. It is just that our minds have not yet taken the last hypothesis for solving this. Another opportunity is that there is a multiverse located in all practices of coexisting but non-communicative cosmo. There is an endlessness of choices, but nearly all of these are contrary to the development of life. too hot, too cold, too bumpy, too smooth, too modern, too ancient, and so on. Consequently, Arizona State University physicist and author Paul Davies has denominated the Goldilocks enigma. Our proximity selects just one cosmos as observers. Such multiverse hypotheses are claimed to be, writes philosopher Neil Manson, the ultimate resort for the acute atheist. More effectively, the underlying physics is inadequate. We certainly have no sense if the many so-called scenes in the multiverse can be populated by Pocket Cosmo, as its citizens are called, the continuation of a bio-friendly cosmos as a hugely remote event that does seem to require an answer. One alternative is to advance to a higher authority or creative design to justify our behavior. This clears up the question of who created the designer and why. Nor does it differentiate monotheism from Valhalla, the field of the gods in Norse mysticism. While this resolution is a supported conference stopper for science-minded personalities, the options do not stop here. Possibly the cosmos is a vast Gaia-like entity, named for Gaia, the Greek goddess of strength, with built-in awareness of its mission. Alternatively, perhaps we are dwelling in a Matrix-like supercomputer simulation. One might assume that Hollywood came closer to the fact than the most eminent string theorists who string theory to reveal quantum gravity. This must not confuse anybody. There is one answer that I find most appealing. Suppose the cosmos was eternal. All bets are off in this instance, because it is reasonably challenging to calculate the chances for or against life. In an infinite cosmos, the most extraordinary events occur someplace. Furthermore, here we are in our bio-friendly pocket cosmos. Perhaps what is most remarkable for the physicist is that this metaphysical solution of an eternal universe can be experimentally testable, at least in teaching. Such tests primarily involve reading the abundant angular scale characteristics of the cosmic microwave background and increasing the accuracy of the universe's curve measures, the frontier boundaries of the multiverse. We know the Earth is not flat because no one has described hanging over the edge. The fullness of the Earth restricts its size, giving it a boundary that cannot be bisected. We can take a similar line to the multiverse, a proposal that purports to describe many of the so-called eventualities in nature beyond certain borders. In nature, drastic changes take place. Many of those changes could be a disaster for human reality, preventing it from taking place. Furthermore, those differences in which this kind of approach has entertained the rules of possibility push us approaching the most critical space conceivable. For example, we demand to know why the proton mass is only somewhat more significant than the neutron mass. This size difference coincides with the measure of the hypothesis of electroweak interactions. If it were yet insignificantly different, stars would not work. So, we are destined to be pushing against this critical limit. The proton-neutron difference is cramped to what is perceived. If ordinary stars subsist, let us proceed farther the rules of possibility. These show us what is plausible and what is not. Cosmologists who see a rigid frame that classifies various ranges of values for the necessary constants may claim that related logic might separate Cosmo. At the slightest, one of these holds galaxies in the standard view. Galaxies produced from minute variations grow more potent by gravitational growth. These are overcome. If the cosmological constant is too great, galaxies will not grow. It is an all-or-nothing prospect. Observers populate universes. The ominous tragedy of no stars, no galaxies, faced with the influence from the multiverse, isolates us at the edge of the multiverse where circumstances are just average. The advantage of the catastrophe approach is that it sets a firm line in superspace. The new ridge in this view, presented by Lawrence Hall of the University of California at Berkeley, is that the organization of multiverse pressure and catastrophic limits illustrates many of the fine tunings observed in life. Are we normal, or are we a cosmic fluke? Here is a different way around the Goldilocks dilemma. Maybe we are far from ordinary observers of the cosmos. It has been shown that quantum theory cannot expect us to be everywhere with high probability. The Copernican principle that the Earth is not the heart of the cosmos returns with a retaliation. Our very survival could be an incredible event. American physicists can determine that it is quite conceivable and not significantly unlikely for us to exist in a cosmos where we are not expected. Cosmological models that foretell that at most limited one example of complicated data exist with possibility somewhere in space-time are interchangeable despite how many other specific copies exist. This leads to enormous suggestions. Trials in cosmology might become irrelevant because there is no relevant similarity between us and how the cosmos seems. Canadian cosmologist Don Page settles those observations would score for nothing in differentiating between hypotheses, and much of cosmology would terminate to be an observational science. Now there is a different understanding of that heartless redneck theory. We would no longer be authorized to use odds, that is, chances, to see between cosmo. What difference would it perform if our cosmos were 1 in 10 to the power of 500? If we could no longer discuss whether this was likely or unlikely, it had to appear somewhere, and it might also be us. This sort of argumentation puts an end to the anthropic principle's naive forms, indicating our unique place in the cosmos. The anthropic observer's role can be examined more intensely as well. Perhaps there are practically no observers. It may be that all but a few of the 10 to the power of 500 voids that populate the panorama are completely unpopulated by spectators. Physics is unnecessary, since quantum theory needs observation for the truth to be visible. In this experiment, Pity Schrödinger's cat was identified for the thought exercise of the German physicist Erwin Schrödinger. The cat is in a case and permanently sentenced to be both alive and dead in a dual virtual reality until the inspection order by opening the box is completed. This heads to one of the most well-known mysteries in quantum theory. The relief of poison gas was triggered in the cat's box by a radioactive disintegration intrinsically probabilistic. The decay transpires, or it may not, but there can be no doubt once the cat's case is open. It is either living or lifeless. Physicists struggled to explain this by assuming that there are 2 cats, one living, one dead. Only one of these unpredictably actualizes when the case is opened. We get into this predicament because the spectator takes him or her away in the cat's state no longer values. The equivalent could be true for nearly all our toxic cosmo. They are barren of spectators in physics articles. The rolling field, which applies the void state into a cosmos, rolls so gently that it just appears at its target. Only the longest-lived cosmo get populated. One of these is ours, easily old enough to produce stars. If simply one cosmos made it to this coveted state, we would be given far fewer opportunities to define our continuation. This way, we bypass what has been called the young Ness paradox. Why are we so young when unbelievably many more cosmo are far more experienced? Of course, there might be other options, such as cosmo with various states of the basic constants. These cosmo would not yet make stars. There would be no other separate universes. Nevertheless, at most limited, there are fewer of them. Our resort here may be to assume that an advanced physics hypothesis will present values of the material constants. We are in a great fellowship, after all, Eddington imagined. So he measured the precise formation constant to various vital figures from the first principles. Nevertheless, he frustratingly received the wrong answer. Defying our biggest challenge, dark energy counters cosmologists from relaxing at night. Why is its body so small when all particle physics theories lead us to a state more monstrous by 120 factors usually? There is one argument on the strength of the force of dark energy that merits serious attention. Furthermore, Why is it presently working to dominate the universe's development as hurrying is driving over? Physicists dislike the concept of fine-tuning their explanation for choosing what seems an unlikely event. Hence, they have grown up with a proliferation of multiverse considerations. These stink of metaphysics and are irritable to verify science fiction-like progress in time travel technology. They are still challenging to lie with any foreseeable investigations. Nevertheless, it reveals why dark energy needs to be small and analyze its results. When we measure density inhomogeneity in the cosmos, we draft them within the temperature variations seen in the microwave background. The level of the variations is negligible. It amounts to 0.001%. If Einstein's cosmological constant, the most simplistic display of dark energy, was greatly more critical than the determined value, galaxies could not have developed from these fluctuations. However, we live in a galaxy, and we would not be hereabouts where there are no galaxies. Therefore, there is an observational prejudice in our considerations. Our residence demands a low value and modern control of dark energy. Of course, one might ask why there should be some dark energy at all, and galaxies are excellent in a cosmos without dark energy. Here, the evidence for a cosmological constant, and hence for dark energy, arises from string theory. String theory is speculation of quantum gravity. It tries to illustrate how the most diminutive and most significant powers in the cosmos and all significant interactions were once joined in multidimensional lines before the Big Bang. There are many potential benefits for the strength of the dark energy force. The most likely value is where the number of model choices is most meaningful. This is the most outstanding value. Nevertheless, this influence toward bigness is defined by the requirement for us to observe dark energy and, more particularly, to exist in a galaxy. Therefore, dark energy is necessary, minor, and only freshly authoritative. Nobel laureate physicist Steven Weinberg first read this case for the smallness of dark energy. There are at most minuscule two structural imperfections in this thought. One approaches from statistics. The thoughts always follow the rules of the Reverend Thomas Bayes, namesake of Bayes' doctrine. This 18th century statistician stimulated a new form of computing, the chances of an incident transpiring, studying all potential theoretical circumstances. The more significant the possibilities, the more apparent it is to promote one of these selections. So we require total witnesses. It sets out that if one concedes for the actual number of observers and the future, in any given cosmos, the chances shift dramatically. Infinity forever wins when employed. Bayes' system promises that near-zero dark energy cosmo are valued. There are far more universes per unit volume connecting all the cosmo with zero and minimum dark energy than those with high dark energy. So the higher fixed on dark energy persists, but there is no longer any predictability. There should never be dark energy. Our efforts to determine anticipated amounts of dark energy only worsen. Even the higher tide on dark energy is not a sturdy discussion. Here is why. If variations could be significant originally, this would reduce the force on dark energy. The general study says that enormous black holes sooner than galaxies would set quite shortly in the universe. However, this analysis implies that the primordial fluctuations are generated by enlargement using the enlargement field. This is an energy field with no favored way. We describe such an energy field as a scalar field rather than vector fields of energy directed. This field provides the energy that produces extension and causes the quantum variations that seeded galaxies and are perceived in the microwave sky. The varieties are like advancements in matter and radiation. If two giant black holes would generate and eventually govern the cosmos, this is not the crisis. Any argumentation about expansion has loopholes. One is that there is no single energy field that drives expansion. String theory determines that there would be a comprehensive slew of scalar fields. The conclusion is that the most basic primordial settings consist of two different varieties. One follows to the concentration of material and radiation. This amounts to a small rise in the local curving of space. Einstein shows us that this excess gravity ultimately causes galaxies to deflate once the cosmos is cooled down and is controlled by conventional matter. These are the variations expected if a single scalar range stimulates expansion. There is now a different type of variation in which an underdensity counterbalance for an overdensity material in radiation. There require no longer be a simple curvature inconsistency at all. There are even variations with zero deflection. The title claviton has been assigned to the organization of fields that can produce zero curvature variations. Moreover, because the radiation frequency is so tremendous early on, one can compare this with an enormous material fluctuation. Great inconstancies in the material are reasonable, but because of the scales with radiation pressure, any chance of early black hole production is bypassed on the orders of galaxies. The variations could be more meaningful by some 20 factors than the natural curving fluctuations and still head to pleasant microwave background temperature ripples. Galaxies would form fresh as shortly as the cosmos consisted of thermonuclear hydrogen and the radiation finished strewing facing the electrons. This lasted 1 million years following the Big Bang, but the galaxy mass veils would develop and form stars. The resulting cosmos would not be a reproduction of what we perceive. Nevertheless, this barely matters. The arched cosmos would include an abundance of galaxies, stars, and planets. It could hold a far more substantial dark energy content than our perceived universe. It would unavoidably carry observers. We cannot apply galaxy formation to produce any significant pressure on dark energy. Mathematics may have the ultimate say in picking our cosmos. Possibly specific rules of mathematics that work in the most profound regions of existence have directed that we have the cosmos we hold such proof would create an impregnable event. The conventional form of particle physics is a crucial component of string theory, which, as seen earlier, is a hypothesis of quantum gravity. One-dimensional waves paint particles in a greater dimensional field. Strings subsist in a 10-dimensional hyperspace. This presents a mathematical description of all of particle physics. Particle masses are essential to the hypothesis, as is supersymmetry. The hypothesis is still unfinished, but it performs the most compelling story of the universe's beginning. Supplied with string theory, one obtains a certain number of potential geometric spaces, either one of which could ultimately compact Alpha into our cosmos. If we use supersymmetry as our guiding system, there are 10 to the power of 500 of these places called Karlovy-Yale manifolds. Each is a forerunner position of a potential cosmos. Each concedes 3 generations of particles. Therefore, all associated particle physics can be included in every one of these manifolds. The cost one gives is that all holds 6 dimensions. These subsisted at the Planck moment at the universe's origin, when gravity was associated with the opposite significant forces. This was the tale of quantum gravity. Our universe has 4 dimensions, 3 in space and 1 in time. As the cosmos unfolded away from the planet density and chilled, the gravitational communication became much smaller than the nuclear forces. At the same time, the additional dimensions contract challenged one of the manifolds that became our cosmos. There may, however, be evidence on microscopic layers of protected dimensions. These would show themselves as tiny variations from Newton's rules of gravity on microscopic scales. Physicists are hunting for such conclusions, but have not encountered any. There may also be evidence of hidden dimensions on gigantic measures. Not all thought of the Big Bang universe local been deleted by the condensed application. Again, no notable differences from Einstein-Newton's gravity have so extensively been seen. How do we organize the excess of early cosmos? The scientific hypothesis is that there need be a sort of topological similarity to a viable form. You have been listening to Mysteries of the Cosmos, challenging enigmas that astrophysics are trying to solve.
Marina, Tura Laraba, Kopana, Lana, Tula. Marina, Lana, Marina.